So in part 2 of our Food, Fuels and Energy Systems PowerPoint, we're going to focus just on our energy systems. And we have three main energy systems that we use to make ATP, being the ATP-PC system, anaerobic glycolysis, and then also aerobic energy system. So the deal is that ATP is the only fuel that the muscles can directly use for muscle contractions. We store ATP in the body, but we can only store enough, it's about 50 grams, which is enough to fuel maximal intensity activity for about 2 to 3 seconds. So as soon as that 2 to 3 seconds is up, then we rely on our energy systems to resynthesize the ATP so we can keep performing. We talk about there being an interplay between the three energy systems, and to be honest, the questions about energy system interplay are the most common ones in your VCAR exams. Expect one in a SAC as well. And they're the harder things to talk about when it comes to the energy systems. So we'll focus a fair bit of time on them down the track, and particularly in class. But what we mean by interplay is just the fact that the systems don't work in isolation. It's not the case that just one particular system fuels a particular activity from start to finish. It's also not the case that one system starts and then stops, then the other one starts and then stops, then the other one starts and then stops. But it's more the case that at the start of exercise, all three systems are activated and all are contributing to the production of ATP. But what we do say is that at any one time, one of those three energy systems is the predominant energy system contributing to ATP production. And the things that determine which system is predominant at any one time are these 4 points down the bottom. So the duration of the activity, so how long it lasts for, the intensity of the activity will also influence which system is predominant, whether oxygen is present or not, which is more a case of whether you're getting oxygen to the muscles at a fast enough rate in which you need to use it to produce ATP. And if you're not doing that, then you're working anaerobically. And also depletion of chemical and food fuels. For example, if all of your phosphocreatine supplies are depleted, then your anaerobic glycolysis or aerobic energy systems would need to be used. So those four things are the things that determine which energy system is the predominant energy system contributing to ATP production during the interplay between the three energy systems. So the first energy system we're going to look at is our ATP-PC system, which you can see up here. Sometimes it's also called the ATP-CP system. This is your predominant energy system in maximal intensity events that are lasting, well, less than 10 seconds really. So it's an anaerobic system, so it does not require oxygen in its processes to break down phosphocreatine to produce ATP. So any activities that are carried out above your VO2 max are going to be fueled by the anaerobic energy system, and this is an example of one of them. So in terms of comparing it with the other systems, and this is what VCAR like us to do, is often compare the rate in which the ATP is produced, compare the yield of ATP, so how much of it is produced and therefore how long can it sustain physical activity for, the fuel source that is broken down, and if there's any fatiguing mechanisms. So compared to the other two systems, the ATP-PC system is the fastest at producing ATP, and that's why we use this system to fuel our maximal intensity activities, because the higher intensity you work at, the faster you're using ATP, and this is the fastest system to replenish that ATP. In fact, with the ATP-PC system, it will resynthesize ATP at the same rate the ATP is broken down. So this is definitely our fastest producer of ATP. However, it also has the lowest yield of ATP. So because of one molecule of creatine phosphate, you can only make one molecule of ATP. And we store creatine phosphate in our body, and we have a pretty limited supply of creatine phosphate. So there's actually only enough for us to make the amount of ATP that will sustain maximal intensity exercise for about 6 to 10 seconds. So the fastest producer of ATP, but produces the least amount of ATP. How does the process work? It actually is incredibly similar to the way that ATP itself works. So ATP snaps off its last phosphate to release energy, and then that energy is used for muscle contraction. With the ATP-PC system, you have a molecule called creatine phosphate, which is essentially a molecule of creatine bonded with a single inorganic phosphate. That molecule snaps off that phosphate to produce creatine on its own, and then the inorganic phosphate on its own. The bond that we had between the creatine and the phosphate stored energy. So by releasing the phosphate from creatine phosphate, energy is released, and that energy is used to resynthesize ADP plus PI back into ATP. So as a final summary, ATP-PC system, its fuel source is the chemical fuel creatine phosphate. Its yield of ATP is the smallest, and it's 1 ATP per molecule of creatine phosphate. The intensity of activities that use this system predominantly are our high intensity activities above 95% of max exercise. The speed of ATP production is the fastest, and in terms of fatiguing mechanisms, it doesn't really produce any byproducts that will cause your body to fatigue. Fatigue more comes as a result of depletion of the fuel source, which is the creatine phosphate, because as I said before, it's stored in pretty limited supplies. As a benefit though, it's stored in the muscle, which is why it can also have such a fast rate of ATP production, because it's already at the site of where we need to use it. So our second energy system we're going to look at is anaerobic glycolysis. And as the name suggests, just like the ATP-PC system, it is an anaerobic system, meaning the production of ATP in the absence of oxygen. So we're still talking about fueling activities that are above our VO2 max. So the types of events that would use anaerobic glycolysis as the predominant energy system are once again your high intensity activities, but this time they would be a bit longer in duration than those of the ATP-PC system. So any high intensity activities lasting less than 10 seconds, predominantly fueled by ATP-PC. Any high intensity activities above VO2 max that last for over 10 seconds and up to about a minute, they're predominantly fueled by anaerobic glycolysis. So 400 meter track sprint would be a perfect example. Good runner your age would do that between 50 and 60 seconds. 100 meter freestyle swim, or the 1 kilometer track cycling event. In comparison to the other systems, we would say anaerobic glycolysis produces ATP at a fast rate. So it is a fast supply of ATP, but it's not the fastest because it doesn't produce it as fast as the ATP-PC system. But it certainly does produce ATP faster than the aerobic energy system. As I said before, in terms of yield, its yield is still relatively low. So per molecule of glucose, you make 2 molecules of ATP. So it's enough ATP to fuel activity for 30 to 60 seconds. Now, the main fatiguing mechanism in this case is not so much running out of the food fuel, which would be glucose, but it's more the accumulation of a byproduct in the form of hydrogen ions, which build up in your blood and change the pH to make it acidic, which causes your muscle contractions to slow down by affecting the enzymes. So what does the process look like? So the input is glucose as your chemical fuel. Glucose is broken down through a chemical reaction called glycolysis, and that converts the glucose into what we call pyruvic acid. The pyruvic acid is then further broken down into lactic acid, and lactic acid is broken down into lactate and hydrogen ions, plus energy, because that's the whole point of it. So in the absence of oxygen, anaerobic glycolysis takes place. Glucose is broken down into pyruvic acid. The pyruvic acid is broken down into lactic acid, which exists in your blood as a molecule of lactate and as hydrogen ions. By breaking the pyruvic acid down into the lactic acid, that releases energy, and that energy is once again used to resynthesize ADP plus PI into ATP by supplying the energy to add that phosphate back on. Our overview, so our fuel source is glucose. Our ATP yield is relatively low in 2 ATP per molecule of glucose. Our intensity of activities is still quite high, so if you're looking at all activities probably carried out above 85% of your max heart rate. Duration that it can sustain activity is 30 to 60 seconds. Speed of ATP production is fast, but not the fastest. Fatigue is once again not so much due to depletion of a fuel source, but this time it is due to the buildup of a byproduct in the form of hydrogen ions in your blood that make your blood become too acidic. That puts your enzymes, the things that fuel all your chemical reactions, out of their optimal zone, and therefore they don't work as efficiently, and your muscles stop contracting as frequently and as forcefully, and your performance slows down and you fatigue as a result of that. Our final energy system is our aerobic energy system, and as the name suggests, this is our energy system that requires oxygen to be present for this energy system to produce ATP. So events that would use the aerobic energy system as the predominant energy system are all of your submaximal intensity activities that go beyond 60 seconds. So any activity that lasts for more than 60 seconds, continuous duration, post 60 seconds, if it lasts for 70 seconds, then you're going to be saying your aerobic energy system is your predominant energy system. In comparison to the other energy systems, the aerobic energy system is your slowest producer of ATP. So this process, and you can even tell by a sneaky look at the diagram at the bottom of this page, it has heaps more steps. So if you think of ATP-PC system had essentially 1 or 2 steps, anaerobic glycolysis had a few steps, aerobic energy system has quite a few steps. The more steps, the longer it takes. The longer it takes, well, the slower the production of the ATP. So although it produces ATP at the slowest rate, it does produce the highest yield of ATP. So this time, per molecule of glucose, the exact same molecule of glucose you could use in anaerobic glycolysis, this time you're getting 36 to 38 ATP molecules off that one molecule of glucose, whereas back in anaerobic glycolysis, you were getting only 2. So it's a slow supply of ATP, but it's a large supply of ATP. And essentially, providing you keep fueling your body, it could fuel activity, non-stop, endlessly. There's no limit. You could just keep going and going. Let's have a look at the process. So as I said, oxygen needs to be present. And in the presence of oxygen, what we do is we take glucose. It once again is broken down into pyruvic acid. But whereas in anaerobic glycolysis that pyruvic acid was converted into lactic acid, this time it's not. It's converted into acetyl-CoA. That is essentially converted into carbon dioxide. As a byproduct, we also produce water and we also produce energy. So we will go through this in more detail in class. And any of you that have done biology at VCE, this is aerobic cellular respiration, and you'll be able to fill in a lot of the gaps. So recap, glucose is broken down into pyruvic acid. That occurs in what we call the cytosol of the cell. Within the mitochondria of the cell, which is where most of aerobic respiration takes place, the pyruvic acid gets broken down into acetyl-CoA. It gets broken down into carbon dioxide. In the process, we produce water as a byproduct, and then we produce energy. And the energy is used once again to add the third phosphate back onto ADP to form ATP once again. However, if there's no oxygen, then this won't happen. The pyruvic acid will get converted into lactic acid. That's what happens if there's no oxygen. These final steps from acetyl-CoA onwards only occur when oxygen's present. You can see down the bottom of this diagram I've also added in fatty acids. So you might remember that fats are also a food fuel, and you hopefully might also remember that fats can only be broken down by the aerobic energy system, and that process is called beta oxidation, or it's also called aerobic lipolysis. And what happens is the fatty acids get converted into acetyl-CoA, and then the rest of the processes are the same. You might also remember, by breaking down the fatty acid compared to the glucose, we will produce a lot more ATP, but it will also require a lot more oxygen and will also take a lot longer. So, summary, fuel source is glucose and could also be fatty acids, but glucose is preferred energy source. Yield of ATP is 36 to 38 molecules of ATP per molecule of glucose, so a high yield. Intensity of activities, we're talking about submaximal intensity, so activities below 80% max heart rate. Duration, all activities lasting past 60 seconds, and that can go up to a matter of hours. Speed of ATP production is slow, the slowest out of all three energy systems. The fatiguing mechanisms aren't going to be the byproducts like in the anaerobic glycolysis, but it would be the fuel depletion. So you will get to the point where you deplete your glucose levels. When that happens, you'll start breaking down your fatty acids, and because it takes longer, you'll see it in your body as fatigue because you won't be able to perform at the same intensity. So if we have another chat about energy system interplay now, which I said before is a really important concept and one that's generally examined reasonably heavily. What I mean by that is there's always a question on it in every exam. It is a topic that definitely needs to be unpacked in class, and we'll do that in class for sure. But as a simple overview, this is a pretty typical graph you would see talking about energy system interplay. And what we see that as exercise starts, so max intensity exercise starts, even submax intensity, as at the commencement of any exercise or physical activity, all three systems are activated. So ATP-PC, anaerobic glycolysis, and aerobic energy system. So all three are activated as soon as exercise starts. If we assume it's maximal intensity exercise, then it's going to follow this trend here. Though all three energy systems are contributing to ATP production, the ATP-PC system would be contributing the most ATP to fuel the activity for the first 6 to 10 seconds. After 6 to 10 seconds, the stored creatine phosphate in your muscles will be depleted, and then the anaerobic glycolysis system will be the predominant contributor of ATP to fueling that maximal exercise for the next 30 to 60 seconds. After 30 to 60 seconds, the hydrogen ions, which are the byproduct of anaerobic glycolysis, will have accumulated to high enough levels in your blood to be a problem, to be causing fatigue and trigger your body to say, hey, we can't change our pH more than this. Stop making ATP in this way. So after 30 to 60 seconds, then the aerobic energy system will be the predominant contributor to the production of ATP up until the next 3 or 4 hours. If exercise continues after that point, the aerobic energy system remains the predominant contributor to ATP production, but after the 3 to 4 hour mark, glucose levels would be depleted, and then the fuel source would have shifted to fats. What this graph is showing us is that each time we shift to a different predominant energy system across the course of that maximal intensity exercise, we get a decrease in power. So at the very start of that maximal intensity bout of exercise, our power output is at its greatest, and that's because we're using our stored ATP. So we're supplying the ATP needed for muscle contractions instantly. After 3 seconds, when our ATP stores are depleted, we shift to our ATP-PC system to regenerate ATP, and we get a drop in power because although it's a very fast system, it still can't produce ATP at the same rate as which it was supplied to the muscle when we already had it there in the first place. So it takes a little bit longer to make the ATP, so we get a decrease in power because it's not supplied as quickly. Then we drop down to anaerobic glycolysis, and compared to the ATP-PC system, it does not supply ATP as quickly. So once again, we can't give it to the muscle as quickly, so we have another decrease in power. Same thing happens when we drop down to the aerobic energy system being predominant. It's the slowest producer of ATP, so that results in a slower supply of ATP to the muscle, so another decrease in power. And then we get a pretty big decrease as we drop down to fats as the main fuel source during aerobic energy system, because as we all know by now, it is a slow process breaking down fats, so you're supplying ATP to the muscles at a much slower rate than all of the other energy systems. So throughout the duration of that event, the person's ability to work at maximal intensity, I suppose, decreases each time it shifts to a different predominant energy system. Also important just to point out, this interplay does depend on the type of exercise being undertaken. So we've talked about max intensity exercises. If we were talking about interplay during something like a marathon, which you'll do in your next couple of slides on, it's still the case that all three energy systems would be initiated at the start of the marathon. But for example, the anaerobic glycolysis system might not fuel the first 60 seconds of exercise because the intensity is such a rate that it might only take the body 20 seconds to get to the point where it's supplying oxygen at a fast enough rate for aerobic cellular respiration, or the aerobic energy system, to kick in. So if it's submaximal, those anaerobic systems will be the predominant energy systems for less time, and the aerobic energy system will kick in sooner than the 60-second mark. So if we have a look at a scenario, and that's another thing that you might get asked to do in a VCAR exam or in one of your SACs, is to analyse the interplay occurring in a scenario. If we take an intermittent activity, something like netball, where you're not constantly running the whole time, but there's going to be small stoppages, there's going to be short bouts of sprinting, there's going to be short periods of walking or running at a low intensity. This is generally what you would see. So like all activity, as soon as the game starts, all three systems would be contributing to ATP production, but the ATP-PC system would still be the predominant system for the first 6 to 10 seconds. Following the 10 seconds, the anaerobic glycolysis system would be the predominant contributor of ATP. And then we say that maybe around the 2-minute mark, the aerobic energy system would become the predominant system contributing to ATP production. Why is it 2 minutes when up until now we've been talking about 60-second mark being the main indicator of change? Well, you're assuming in that first 2 minutes the athlete's not sprinting at max intensity for 2 minutes straight. They might have a short sprint and then they might have a break. Then they might have another sprint and then they might have another 5-10 second break. And even though they're not significant breaks, they're still going to be long enough for some of the phosphocreatine stores to replenish. And they're also going to be enough time for some of the hydrogen ions produced in anaerobic glycolysis to get removed from the blood and put the blood pH back to where it needs to be. So with those short little periods of recovery, if you like, the aerobic energy system probably wouldn't kick in to being the predominant system until about 2 minutes. However, after the 2-minute mark, no matter what that athlete does, the aerobic energy system will remain the predominant energy system. And it would be like that until there was like a decent break, like quarter time, where the ATP-PC system could fully replenish and a lot of the metabolic byproducts from anaerobic glycolysis can have sort of been washed away from the blood. So yeah, as I said, aerobic energy system remains predominant after the 2-minute mark up until a very decent stoppage in play. During that, let's say the quarter goes for 15 minutes, from the 2-minute mark to the 15-minute mark, you are still going to have bouts of high intensity efforts where the netballer is sprinting at max intensity. And as soon as they're doing a high intensity effort, they're requiring more ATP. So what enables a person to have a surge or a short bout of high intensity effort is an increased contribution by one of the anaerobic systems or by both of the anaerobic systems. So during a surge in a race or during a sprint bout in a game of netball, after that 2-minute mark, the aerobic energy system is still the predominant energy system, but the anaerobic systems have increased their contribution to sort of fill that void or create that balance of ATP that's required for that short, sharp bout. If we look at a different example and the interplay during a marathon, it starts the exact same way. At the start of activity, all three systems are activated. And once again, the ATP-PC system is the predominant system for the first, well, we say 6 to 10, but in this stage we can say 8 to 10 because you're not going at max intensity, so you might get a bit more duration out of it. But still, nonetheless, for the first 10 seconds, ATP-PC is predominant energy system. Once again, after that 10-second mark, the anaerobic glycolysis system will become the most predominant energy system. But this time, it's not going to be predominant for the up until the 60-second mark or up until the 2-minute mark, like we saw in the netball. Because we're at a submaximal intensity, the aerobic energy system will get the supply of oxygen it needs sooner in the race, and it will kick in as the predominant energy system pretty quickly after that race starts, so within the first 60 seconds. From that time on, the whole duration of that race, it doesn't matter how that athlete runs, how many times he surges and increases his speed, aerobic energy system will remain the predominant system for the whole entire duration of the race. Because it's a continuous race, ATP-PC system won't have that passive recovery time to replenish, so it'll be done after the first 8 to 10 seconds. It won't contribute any further throughout that marathon. Obviously, throughout the marathon, the athlete is going to have periods where he surges and increases his running speed for short periods of time. And what enables him to do that is getting an increase and faster supply of ATP to the muscles for that period of time. And that comes from having a greater contribution during the surge by the anaerobic glycolysis system. However, that's all it is doing. It's just increasing its contribution. It certainly does not become the predominant energy system at any time during the rest of that race. Aerobic energy system remains. Because it's just a surge or a number of surges throughout the race, that surge will be followed by a relatively low intensity period. And during that lower or to moderate intensity period, we're actually able to take the hydrogen ions that had accumulated during the surge from the anaerobic system, and we can convert them back into glycogen whilst we're exercising at that lower intensity. When it comes to targeting each of the energy systems through training, you want to tailor your training to the characteristics of that energy system. And this is a really brief slide, but we'll cover training principles later on in the course. If you're going to be training your ATP-PC system, while you're doing short interval training or you're doing explosive short duration training like plyometrics or resistance training with a pretty low amount of reps. So your intervals would be, you'd have a period of max intensity exercise for about 10 seconds, because that's the amount of time we can fuel activity using the ATP-PC system. But you would follow it with a lengthy recovery time, 3 minutes for example, or a minute if it's only been a 5-second bout, because that's the amount of time needed for the PC stores to replenish. So then you've got them almost back up to 100% to then do your next interval. Anaerobic glycolysis, once again you would be doing interval training, but this time it would be a slightly longer interval, so 30 seconds to 90 seconds. Once again, that's the period of time where the anaerobic glycolysis system is predominant. And once again, you would follow that bout of exercise with a suitable recovery time, maybe 3 times longer or twice as long as the bout. And that recovery time would give you time to get rid of some of those metabolic byproducts in the form of hydrogen ions, convert them back into glycogen, so that then at the end of your recovery, you can do another all-out effort within your anaerobic glycolysis system. The aerobic system, once again, you can do interval training, but it would be long interval training, and your recovery period would be less than your exercise period. So your work to rest ratio, your work would be higher than your rest. Or you could also do continuous training, and you'd want to be doing that for at least 30 minutes if you're doing moderate intensity. And a little note down the bottom, anaerobic glycolysis system has the greatest capacity to improve with training. Your aerobic system has less capacity to improve, but you can improve your performance, your aerobic performance, by increasing your anaerobic threshold through anaerobic training.